Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome back to day 57 NL Math Man's Math Help Streams. We're here, the same math time and the same math channel. That's right. Above me here today now, we got a very nice picture. Oh, every day it's a very nice picture, right? But today it's like an especially very nice picture. This is a rare summery shot. Flurry and Smokey out trotting around in some water. Again, I can't recall where this one is. This is not by the cabin either. I know that because the pond out by the cabin is very silty on the bottom and is covered with like old logs and stuff because it used to be a sawmill, like I explained before, right? It's not rocky at all like what we see here. What we see here is very clear and very rocky, and yeah, I can't quite recall where this picture is taken, but either way, it's very sweet. Look at little brother going to give little sissy a big kiss, a big lick, Bigglick, big lick. He often he cleans out her ears and her eyes, right? No, apparently it's a deferential thing for dogs, right? Like if the other dog is the older one, right? You show your affection sometimes by cleaning out their ears and their eyes because they can't do it themselves, right? So like you know how like little bits of crusty sleep sort of form in the corners of dogs' eyes, right? Smokey cleans that out for Flurry, and then someone else like me has to clean them out of Smokey's once because she doesn't really reciprocate the same. Hey, Spiridon, Spiridon, I think that's right. Hey, how's it going? Welcome to the math stream. Just talking a little bit about my background for today. Now, before I get into the math that I'm going to start off with, you can see Smokey's coloring a bit better here than in the other pictures that I've shown, right? Like depending on the lighting, he looks more or less like a third run, right? In this shot, he looks very much like a third run because you can see the much lighter sort of mane compared to his dark muzzle, right? For today, for the math, I am going to get into, we see over here, right? Going to get into some counting problems recap. So Calais, that'll be for your course. It's just a really quick recap of some of the ones from the recent activity that you did. Then I will get into an introduction to probability. Now, Calais, that is for your course as well. That's the next section that you're getting onto. Uh, that one, yeah, it's not a super difficult intro. I mean, you haven't asked any questions about that yet, so you might be good to go. I am just going to touch on those different terms, though, experimental versus theoretical for probability, and then odds for and against. It's really just a minorly different way of representing probability, basically. Then Renetta, I'm going to do a bit on Pythagorean theorem for your course. You mentioned that you were still working on that. Um, yeah, but I guess if I've linked this to you in the future and you're watching it on a VOD, then you're not really hearing this first part. I guess you probably skipped ahead to the part where I do your questions. But anyway, so that's the itinerary for today here on day 57 of my math stream. Right, week 12. Week 12 is almost down. Boy, boy, oh boy. I'm going to pop over here now to my. There we go. This is the first topic that we're going to do. And anyone in chat, of course, like if you have any questions about the math, do feel free to drop that in, and I will get to those, of course. This is math. What was this course number? Right, this one is 3101, 3101A still, and this is going to be Unit 2. Just the last little bit here in 3101A, Unit 2 for Calais before we move on to Unit 3. Let's see, I'm going to do number 17 and number 23 off of this activity that we see over here on the right. So number 17, how many different arrangements are there for the word arithmetic? Okay. So now I do recall that you approached this question correctly, right? We start off with putting down sort of a section for each of the letters, right? So how many letters do we have there in arithmetic? Well, we've got, oh, let me see. Let me get my cursor on the one where you guys can see it. 1, 2, 3. Oh, let me highlight them. Actually, you know what? I'm just going to write it out. ARITHMETIC. Aha. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters in total. Right? So we have a situation where there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we're told in part A that it needs to begin with an M and end with a C. Right? So we know there's going to be an M here, and there's going to be a C over here. Which if we go back up to the letters, well, what letters do we have left now for the rest of those? Well, this M is spoken for, and this C is spoken for. So we've got arithety to go into this part here, right? Because as far as the order goes, or the number of permutations or combinations, if these ones are static, like this always has to be an M and this always has to be a C, we basically just don't count those anymore. Because since they're not going to change at any point, they're not going to really affect the number of permutations or the number of, well, it is number of permutations, right? Because we are talking about different orders here. Because of course in a word, order does matter, right? So we are combinations. Well, there's only one combination. There's just all of them, right? Because we're not picking fewer than the whole set. But so it is obviously permutations that we're working with here because, like I said, in a word, of course, the order matters. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 items. And then it's important now to remember that we do have to divide, right? We had to divide by the number of letters that are the same. Right? So we've got an I here and an I here. Those are 2, so those are both identical. So we put a 2 factorial down underneath. And then we've got T and a T, so that's another 2. And let's see, there's no second A, no second I, no second H or E. So there we go. Now we just have to go and evaluate what this amount is. I'm going to take a little bit of a shortcut here. I'm going to use my calculator. Right, I got to put the digit in first, the way this calculator works, before I get the factorial. There we go. 8 factorial, 4320. Divide by. Now this is 2 factorial multiplied by 2 factorial, right? 2 factorial is, of course, 2. Right? And this 2 factorial is also 2, right? So 2 times 2 is 4. So it's just going to be that much. Divide by 4. Divide by 4. That is 10,080. So that is the answer for 7A, 17A there. The number of different ways that we're going to, we can rearrange those letters. Now 17B was really the main reason that I wanted to highlight this section a little bit. Right? So if all the consonants are together, so all the consonants, okay, so we've got, the word is still arithmetic. Like so, right? And now what are the consonants in this word? Well, the consonants are all the letters that are not vowels, right? So the consonants are going to be R, T, H, M, T, C. Arithmetic. Arithmetic. I think I've even done this exact one before. I do remember I remember trying in vain to pronounce before, right? Reminds me of the cheat codes in Turok. Boy, I'm really dating myself with that one. Or Turok for the N64, right? Like the ultimate code. You remember what that was? It was all the consonants, none of the vowels, but it was in the phrase, "On the 8th day, God created Turok." And you put all the vowels, all the consonants, the consonants only for that phrase in, and you got like, so you're invincible and like infinite ammo and like all the nonsense. Anyway, so then vowels. The vowels are going to be A, I, E, I. Right. And this was the same time when I did the A-I-E-I-O. Yes. Oh, because Old MacDonald got laid off. That's right. E-I-E-I-O. That's how it goes. That's the rhyme. It's the nursery rhyme for us. The Canadian nursery rhyme. The seasonal workers. Quote unquote seasonal. Quote unquote workers. I mean, does it count as a seasonal worker if just your job closes and it's not really to do with the seasons? They just close? Hmm. It's a good question. It's something for the philosophers of our age to ponder, for sure. Um, so here we have all the consonants are together. So again, sorry, Calais, I'm easily distracted, as you've probably noticed. So I'm going to do the consonants in green. I'll circle those like so. So I'm going to do them in green. So we're going to have 1, 2, 3, 4, 5, 6. So that's going to be one set here like so, right? And then how many different orders are there in this set? Well, there's 6 elements in the set. And are any of these the same? R, well, there's no second R. T, oh, there's a second T. Okay, so that's a 2. H, M, and C. Okay, so there's no second ones of those. So we know here that this one is going to be 6 factorial over 2 factorial. Then we also have our 4 vowels, right? 1, 2, 3, 4 out here. But it's not just the 4 vowels, is it? It's going to be this full set. Because our group of consonants, that can move in around the vowels as well, right? So even though there's 4 vowels, like I mentioned before, there's 5 elements to the set because there's this full set here, the green one, and then there's these 4 red elements and that set, right? So it's 5 factorial over, and again, now we've got 2 i's, right? Most people do, at least nominally. He was really airing his anyway, no, I'm not gonna get into talking about eyesight. Anyway, 2 factorial over 2 factorial. There we go, like that. So we just multiply these guys together. 6 factorial times 5 factorial divided by 2 times 2, right? And that is just going to work out to be, I'm just going to, like I did before, I'm just going to use the calculator over here. 6 factorial, 5 factorial, and this should work. Yeah, divide by 4. No, that didn't quite work. Didn't quite work there for that other entry. 6 factorial, insert, times. Oh, crap. Okay, we'll get there eventually. We'll get there eventually, Twitch chat. So 6 factorial times 5. Holy crap. I'm really Oh, you're not even seeing it. You're not even seeing it. Not even seeing all the incredible fumbling that I'm doing. Divide by 4. Oh, right. That is why did I think that was wrong? 21,600. 21,600. That is correct. Boy. We will get there. We'll get there in the end. You know, sometimes it takes you right up and sometimes down again. Because it ain't easy. It ain't easy. It ain't easy to get to the right when you're going down. Satisfaction, satisfaction. That keep me satisfied. I'm not gonna sing any David Bowie. I promise. I promise. I'm not gonna. Well, not specifically Bowie. Like Bowie would be a fine choice to sing if I was gonna sing something. But maybe I'll spare you singing just in general. Okay, whether it's Bowie or not. Let's see. How many 5-card hands consisting of 3 aces and 2 other cards that are not aces are possible with a regular 52-card deck? Yes. So I did want to show this one as well, right? And it's partly because I wanted to mention again that we need to be, when we're doing questions like this, Calais, we have to be very careful about if we do NCR or NPR, right? And remember that NCR order doesn't matter, right? NPR order does matter. Just give me one quick second. I'm going to grab a deck of playing cards here. Sorry about the noise. Okay, here we go. You'd think I'd have my resources all prepared, right? Well, you you were wrong. So, deck of playing cards. So we're looking for a hand consisting of 3 aces and 2 other cards that are not aces. 3 aces and then 2 other cards. Well, let's make them random, or at least somewhat random. I'll give it a light shuffle. There we go. So we have this hand, right? Pretty solid hand. I mean, any hand with 3 aces is pretty good. I mean, provided that we're playing a high game, right? Like, again, if we're playing a triple draw game, well, if we're playing a triple draw game, I mean, at least we've got a 2 and a 5, right? Like, ace is high in triple draw, so you got to pitch these guys. You just, if you're dealt this hand and at the start of a triple draw low game, you're just kicking yourself. You're like, why am I not playing just like just 5 card draw, just normal 5 card, like in 5 card draw, like with a single draw, trips is like bonkers, right? Because you only get 1 draw in total. Anyway, I don't need to be rambling about poker. But how many 5 card hands consisting of 3 aces and 2 other cards are possible? Well, this illustration that I'm doing here with these cards is just to show, are we going to choose NCR or are we going to choose NPR? So say we had this hand. Is that the same then as if we had this hand? And is that the same as if we had this hand or this hand? Of course it is, right? Like, I can rearrange these cards all I want to in whatever order I want to. The hand stays the same in a relative way. Not even that. The hand literally is the same, right? I don't need to break out like, you know, depressive Pink Floyd quotes all of a sudden. So we know for this question that we are going to use NCR here because the order doesn't matter for our cards, right? Whether we get the 3 aces first or we get them, first, third, and fourth, or we get them all the last 3 cards, it doesn't matter at all. It just matters that we get them. So now we need to use, we know we need to use C. Okay, that's the first thing. And now we need to represent the situation that we're doing. How many 5-card hands consisting of 3 aces and 2 other cards? Well, how do we get the number of 5-card hands? Sorry, I'm getting ahead of myself. That's for the next bit. How do we get the number of aces? Well, there's 4 aces, of course. We know there's 4 aces in the deck, and we're picking 3 of them. Don't mind what I say. Half the time what I say is like just a jumbled expression of all the different things that I'm trying to balance at once. It's a bit too real. 2 other cards that are not aces. Okay, so how many cards in the deck are not aces? Well, of course, there's 52 cards in the deck in total, so there's 48 not ace cards. So it's 48 C2, right? Because the reason we do C here is because there's 4 aces in total, and we're picking 3 of them. It doesn't matter the order. And then there's 48 other cards, and we got to pick 2 of those. So then we got to multiply those ones together, right? So 4C3 is, of course, going to be 4 factorial over 3 factorial, 1 factorial, times, this one's going to be 48 factorial over 2 factorial, 46 factorial. So this is just going to be a 4, and this is going to be a 48 times 47 over 2. Right? So 48 times 47, then times 2. I could do times 4, then divide by 2, but why? It's going to be 4512, like that. Right? So that is the answer for this question. Now, as a way of getting on to the next unit, right? This is the number of possibilities for that hand, right? So to get a hand like this one with 3 aces and 2 other cards, this is the number of ways that can happen. What's the probability? What's the chance? The chance that when you're dealt 5 cards just on the first time, you're going to get 3 aces and then 2 non-aces. How do we find that out? Right? Well, let me just go on over here then. So this is going to be math 3101A, unit 3 all of a sudden. So what's the probability of getting 3 aces and 2 non-aces? Well, we know, right? And this is something that we're going to get into here now in a second. And I think this is a good way of introducing it. We know that probability we find the probability by taking the favorable outcomes and dividing by the total, right? So in this case, okay? So probability is favorable divided by total, right? So in this case, favorable is the number of possible hands with 3 aces and 2 non-aces, like we just found in question 23. That's going to be 4c3 times 48c2, right? And now how are we going to find total? Total is going to be all the possible 5-card hands. So how are we going to find that? We're going to find all the possible 5-card hands. Well, that's just going to be the total number of cards in the deck, which is 52, and then we're picking 5 of them, right? Because it's just 52C5. There's no restrictions on it. It's just the total number of possible 5-card hands that we can get, right? So it's 52C5, which is going to be 52 factorial, divided by 5 factorial times 52 minus 5 factorial, right? I'm just going to go across the page with this just to save myself some room, although, yes, it is sloppy. I should be going down, right? But that's going to be 52 factorial over 5 factorial times 47 factorial, which is going to be 52 times 51 times 50 times 48. Yes, divide by 5 times 4 times 3 times 2. Oh, times 49 times 4. I knew I wrote down something wrong. 49 times 48. My goodness. What am I doing? Times 49 times 48. You know, I notice my own mistakes sometimes. That's the important part. Whoa, that's a big number. But I know these ones are really big numbers, right? Because we've talked about this before, how ridiculously gigantic the total number of cards in a possible hands are, right? But anyway, before actually when I talked about 52 factorial, that was the number of different orders. And of course, in a normal card game, order doesn't matter, which is kind of what I'm beating into the ground over here with this C part, right? But anyway, so we know that 5 factorial is 120. So I'm just going to go ahead and divide that by 120. And we're going to get 2598960. So that 2,598,960, that's the total number of 5-card hands that are possible in poker, right? It's just, or any game using a 52 deck of cards and a 5-card hand, right? So now to find the probability, like I wrote up above here, we've just got to do favorable over total. So that's 4,512, which might have sounded like a large number at the start, right? It might have sounded like a large number on its own, but when it's 4,512 out of 2.5 million or 2.6 million, yeesh, you know, now we're getting it starts to seem a little bit smaller. So 4512 divide by the answer to the last question. That's going to give me 0.0017 I'll call that 0.00174, round it a little bit. We want to make it a percent, and of course we times by 100. So the probability of getting 3 aces and 2 non-aces is 0.174%. So that's the probability you're going to get dealt trips aces right off the start in a game of, 5-card draw or something. Right? It's pretty rare. I mean, that would be the same as any given specific trips, right? But anyway, so that's just a little way to show the link here. And this is sort of what we're going to be getting onto in this next unit, Kelly. Though right from the start, the stuff that I want to get to today in this unit specifically is not quite as detailed as this, what I've done here, but I thought this was a good way to springboard into this discussion. Right, so let me bring up, so this is your study guide here for the next unit. Right, you see over on the side that we're going to get into today talking about experimental and theoretical probability, and then odds as well. So experimental versus theoretical probability is something that you're quite likely have seen before, because this is sort of a grade 12 probability. So this is this is about as complicated as the probability stuff we'll get in our high school curriculum, right? But you've definitely seen probability in other units before this point. And experimental versus theoretical is a topic that has definitely come up. But just to be very thorough, because I do like being very thorough, I'm going to go over these two terms, right? So theoretical probability I'm going to define it a little bit differently than the way your guide does. So your guide calls it the likelihood of an event occurring in theory, which is true, right? That's accurate. But theoretical probability is I like to think of it as theoretical probability is the chance we predict for something to occur, right? So let's say I don't know, let's break out some dice. I haven't shown this on stream much recently. This is my nice dice log. Look at that, right? So that's some good color on there. And the wood case with the, listen to this. Ooh, right? It's magnets. Listen to that again. Ah, yeah, satisfying. Yeah, so this is just a normal case of dice. Say I was just to roll a normal d6, right? A normal 6-sided die. So the theoretical probability of rolling a 2 on a 6-sided die is going to be 1 in a 6, right? For example, because it's just there's there's 6 sides on there, right? And there's only one side that's the one that we're looking for, right? And do remember, like I mentioned before, that probability is always either theoretical or experimental is always favorable over total, right? Divide by total. We'll say probability equals favorable over total. Experimental probability Experimental probability is the chance we observe from having performed an experiment. Let's say I took this die and rolled it, I don't know, 100 times. I'm not going to do that on stream. That would take a little while. But we would then see the different results that we would get from that one. Let me see if do I have. Yes, here it is. Probability simulator. Excellent. Okay, let's do this. Yeah, it's been years since I've used this. I think I used this in high school. Let's try. Let's roll. Now how do I make this roll a whole bunch? Trial set 100. Go. Yes. Okay. And roll. Here we go. Let's see it go. Yes. Look at that. Go calculator go. Okay, this is wonderful. What the calculator is doing here now is it's taking a six-sided die and it's simulating rolling it 100 times. And then we're going to see if we get roughly, we would predict that it's going to be roughly the same result for each of these. Oh, three's in the lead, oh, okay, no. Six, oh, one's pulling out. Oh, okay, we got very even there. Look at that. All right, so it was actually really close in the end for a while there. It was a bit shaky. It was a bit shaky for a bit there. But if we roll the die 100 times, we saw that it actually got relatively close, didn't it? Let's change the number of trials we do. Let's turn the trials down a bit, right? Let's what? Why is this not working? I have to go clear? Oh, I do. Okay. Delete doesn't work. You have to go clear. That's weird. Anyway, back to the program. Okay. So now I'm going to try it again. I'm going to try it again with 10 trials this time. All right, let's roll that die 10 times and see what happens. Oh, it just adds on. Okay. How do I clear this? Yes, clear all the trials. Okay. I see. I see what my problem was. Okay. Now let's go and roll these ones again. Roll a six-sided die 10 times this time. Let's see what happens. Holy moly. Look at that. So we found 2, 3, 4. Right? So we found 4 out of 10. In this case, all right, so this is the one that I'm going to talk about now because this is sort of the sort of skewed example that I was hoping for. Right? So oh, I'll just put it over here. We rolled a six-sided die. And got 4 2s. So oh, theoretical. What am I doing? What am I doing? Our experimental probability is 4 out of 10, right? Because remember, it's always going to be favorable divided by total. Okay? And it is worth knowing a very valid point that I'm going to make, and that we're going to see a fair bit. The fewer okay, so the fewer trials we do, the more likely our experimental probability will differ from our theoretical, just like over here, right? So here we rolled 10 dice, And we found that, well, the 2 was way overrepresented in this situation. Right? Remember before when we rolled 100, it came out very close to the same. So I'm going to go and I'm going to bump this guy up to 90 here now. And go okay, and then I'm going to go back and we're going to add on. Right? We're going to do the same sort of the same thing we did before. We're going to get back up to 100 trials. So I'm going to roll this die now 90 more times. That's a weird language thing. Actually, I noticed that a lot. You know, in North America, we call a singular one, we call this a die, D-I-E, and then 2, this is dice, right? So you wouldn't say a dice, you would say a die or 2 dice. But when I was in the UK, they used dice as singular and plural. They would say 1 dice, 2 dice, right? Red dice, blue dice. It's just a weirdness of English. Okay, so in this case, now even after doing 100, there's still quite a lot of difference. And that's the thing, right? The skew between experimental and theoretical is likely to persist for quite a while. It was a bit curious before when I rolled 100. Not curious, I mean it's totally possible, but it was odd that after rolling 100 before, I ended up with very, very similar. So let's just let that run for a bit whilst I yammer about other stuff and take a drink of water. And I'm gonna crank that crank that one straight up to 500 trials. Let's see how that goes. Let's see if my calculator explodes and overheats. I'm gonna need that liquid cooled TI-84 that they did on Linus Tech Tips, right? Did they actually do that, or is that just a meme? I don't know. I should really look that up. That's definitely my wheelhouse, right? Liquid cool. Well, I don't have a liquid cool computer, though. I don't know. Maybe if I won the lottery, came into a sudden influx of cash, that would be a relatively high priority, I suppose. A real beefy rig. Upgrade from my workhorse GTX 1070. I mean, it just does fine. Like it plays games fine. Although I went and bought a 144 hertz monitor, right? And then I was playing Subnautica there yesterday, and I was only getting like 60 frames per second. I wasn't even getting 144 frames per second. It's like, what's the point? What's the point of having this monitor? Like, I can get 144 frames per second in what, like WoW Classic, right? But who cares? Who cares? You don't need 144 frames per second for a game made in 2006. Although it is nice. It is nice to have that smoothness. Anyway, we're almost there. Calculator's getting there. It's burning through some capacitors here. We see a little bit of smoke coming out of the calculator now in a second, but we'll get there. There we go. So there's our 500 trials. Whoa. Okay. Now we see on the chart here, it is a lot closer, isn't it? All right. It's still not quite there. It's still not as good as that first 100, right? Which is one reason I was a little bit gobsmacked that it just so happened to work out so evenly even after only 100 trials. But now we've done 500 trials and we're starting to see that it's getting a lot closer. But this is experimental probability. Our theoretical is that it should be exactly even between all these 6, right? But even after 500 trials, it's not. And it's probably not going to be for even a while yet. Right? I'm just gonna let that keep going. But my point is, just to sort of show you the difference between these two situations. Oh, did it stop? Is 500 the max? Oh, did I? Oh, I just went to 5. Anyway, I'm just going to let that run for a bit. But we are going to go on now to these questions over here in the book that I mentioned, right? So we've got, let's see here. We're going to do page 141, number 2, okay? So let's go over here, page 141. This is it. And I'm going to do question 2. Sometimes I find that these parts up here are really useful. The way that it's phrased here is a little bit arcane. Actually, no, it's not too bad. Just where it says NS is the number of total outcomes in the sample space. Well, that makes sense. Yes, I mean it is a good way of phrasing it, right? But when it says here that theoretical probability is the number of favorable outcomes for event A, and ns is the number of total outcomes in the sample space. Well, that's why over here, that's why it was 6, right? Because when we roll a 6-sided die, there's only 6 total possibilities. Let's see here. So consider, I'm going to do number 2 here. Consider each game below. Is it fair? If it's not fair, which player has the advantage? And explain, right? Because these are the kinds of questions that are being asked in the book here, right? So I'm going to do page, oh, what is this? What did I say this page was? 141. Okay, so Matt and Pat each toss a coin. If the coin lands as both heads or both tails, Matt wins. If the coin lands as a head and a tail, Pat wins. Okay, so to find out if these ones are going to be fair or not, we need to find, first we need to find the sample space, and then we need to see if it's split evenly between these people, right? So the sample space, well, what are the situations? We're only flipping 2 coins, right? So let me break out these shillings, right? Right, it's hard to see. They're coins, though. I guess I could have used some loonies or toonies, but I spend those, right? Because those are actual money. Right, but then the sample space here, well, we can either have 2 tails, like this, right? So it can be tails and tails, or it can be tails and heads, like that. Or it can be heads and tails, like this. Or it can be heads and heads, like this. That's just it, right? That's all the different options in the sample space. So Matt and Pat each toss a coin. If they land as both heads or both tails, Matt wins. So both heads or both tails, that's Matt, and that's Matt, right? If it lands as the other two, lands as different, that's going to be Pat. Right? So we see that this one is indeed fair, right? Because there's 2 chances that Matt wins and 2 chances that Pat wins. Okay? Yes, I'm actually going to use this now as another springboard here now in a second. I'm going to go down through part B here, and then I'm going to show you how we're going to write these ones out. The way I'm going to write these out is going to correspond to your next unit, which is, or the next topic rather, which is odds. Yes, odds in favor and odds against. So B, I'm going to do this one in red. It's a differentiator from the one above there. So Trina, Lena, and Gina. Excellent. I love it when they rhyme the names. It's perfect. That's good. I don't know why, but that pleases me. Trina, Lena, and Gina each toss a coin. If all 3 coins land as heads, Trina wins. If all 3 coins land as tails, Lena wins. Otherwise, Gina wins. So now we've got a set of 3 coins. Right? So now I'll bring in this other coin that I had lying around, this old 50p. Right? Which is legal tender. So 50p is worth what? Like, oh geez, probably like 80 cents Canadian these days. But you know, these things happen. So if it was all tails, right? So what is it? What is our sample space going to be? Let's find out. All right, so we've got tails, tails, and tails, right? Tails, tails, and heads. Tails, heads, tails. What I like to do is I like to have one like this. Heads, tails, tails. So that's all the ones with 1 head, right? Now let's do the ones with 2. So we can have heads, heads, and tails. Heads, tails, and heads. Tails, heads, and heads. Or all heads like that. Now, I'm just writing out the sample space because this is a relatively simple situation, right? You can, of course, get the sample spaces by doing tree diagrams, but I believe we looked at those ones before in a previous unit. I'm not going to go over the tree diagrams here right now. Now let's see who we have for these ones. So Trina, if all 3 coins land as heads, Trina wins. So Trina is going to win in this case. If all 3 coins land as tails, Lena wins. So Lena's going to win in this situation. And then all the rest of these ones, otherwise Gina wins. Yeah, I think Gina might be bamboozling them. I got to tell you. Right? So, how are we going to represent these situations? We can clearly see that B is not a fair game, right? Because from our sample space, we can see that Lena has a 1 and 8. Okay. Yes, let's do it this way. So over here, the probability of Matt winning was going to be 2 out of 4, which equals 50%, right? And the probability of Pat winning is going to be 2 out of 4, which equals 50%. So we know that, right? And say for this one down here then, the probability of Lena was going to be 1 out of 8. I'm not going to write down the percent for that, but it's 12 and a half, right? The probability of Trina was 1 out of 8. And then the probability of Gina, this bamboozler supreme, is 6 out of 8, right? So this is not a fair game. And this one is a fair game up here, right? Now, what are some ways that we could represent comparing the chances that these guys are going to win? How can we compare the chance for Matt and Pat? How can we compare the chances for Gina, Tina, and Lena? Well, we can compare them using the next topic that we're going on to in this course, which is odds. Okay, so odds are an alternate way of representing probabilities. We show odds with ratios, right? I know sometimes, occasionally, you'll see a course like, well, in the general program, they talk about showing odds as fractions. I really don't like showing odds as a fraction because I think it conflates the nature of what a fraction means. Because to display an odds as a fraction really does not it does a poor job of communicating what the odds are representing because it makes them appear like they are probabilities and not that they are odds, right? So you really need to show the odds with ratios and not with fractions. But anyway, so what I'm going to show you is say odds in favor. So the odds in favor of rolling a 2 on a six-sided die is going to be 1 to 5. Why 1 to 5? Well, because it's favorable to unfavorable, right? Not total, right? That's the difference. So what it's telling us here for odds, in this case, is that there's one chance that we're going to get what we're looking for, 5 chances that we're not going to get what we're looking for. Okay. So the odds against is a ratio of unfavorable to favorable. So odds against is just the same as odds. It's just flipped around. Same as odds in favor. Generally, when people say odds, usually, because you'll notice sometimes I'll just say odds and I won't say odds in favor. And old habits die hard, right? But generally, when we talk about odds, we're talking about odds in favor of something occurring. And if we specify, usually it'll mean we specify odds against. But generally, if someone just says odds, they usually mean odds in favor. But to be very thorough, and for the purposes of this course, we will say odds in favor specifically, right? So So for question 2 on page 141, which we just looked at, what's the odds of Matt or Pat winning? Well, just to show the sheet again, right? So this is the one that we just looked at. We saw that there were 2 chances for Matt and 2 chances for Pat. I'm going to say what's the odds of Matt winning, right? So the odds of Matt winning is going to be a 2 to 2, right? Or 1 to 1, because we can simplify. We can simplify these just like any other ratio, right? So when we did ratio units before, you notice that when you're working with a ratio, you can simplify a ratio kind of the same way that you do, kind of the same way that you do a fraction, right? Right, what's the odds of Trina winning? We see here it's going to be 1 to 7, right? Because there's one case where Trina wins out of 7 cases in total. Odds against Lena winning, 7 to 1, right? Because there are 7 cases where Lena doesn't win, 1 case where Lena does win. It's really all that we're doing when we're talking about odds, right? It's just an alternate way of representing probabilities like these. So I'm almost done with this section here now. Page 148, I'm going to go on to, and we're going to do a question off of this one here. Okay. Yeah, I'm just gonna do one of these ones just for purposes of just moving on more quickly. So I'm gonna do page 148, and this is gonna be number 3. We're gonna do question 3 on page 148. So 3A tells us Lily draws a card at random from a standard deck of 52 playing cards, like Peter has right here. Right? Determine the probability of the card being red. Well, the probability of red, right? The probability of red is going to be the number of red divided by the number total, right? Because of course probability actually, yeah, let's probability is always going to be, of course, favorable over total, right? So it's the number of red over the number total. We know that the number of red in the deck is 26, the number total is 52, so the probability is going to be a half or 50%. Right? So that's all you got to do for those ones. Determine the odds in favor of the card being red. Ah, okay. So now that's a little bit of a wrinkle. So then 3B odds in favor of red, well, that's going to be the number of red to the number not red. Or we could say NR to NR not, right? We could say that. That's going to be, what is that going to work out to be now? So that's going to be 26 to 26, right? Which is the same as 1 to 1, because those numbers are both the same. So the odds in favor of getting red are 1 to 1. We say it's 1 to 1 odds is a phrase you might hear sometimes, which means it's equally likely to happen or not happen. Okay? So then for C, determine the odds against the card being a spade. Odds against spade is going to be, now since it's against, right, we're going to flip the order. If it was odds in favor of a spade, it would be the number of spades to the number of not spades. Well, this is going to be the number of not spade to the number spade, like so, right? We know that a quarter of the deck are spades, and 3/4 of the deck is not spades. So the number, sorry, I need to write that in. So this is going to be 39 to 13, or 1 to 3. Sorry, 3 to 1. My mistake. Okay, scratch that. Or 3 to 1. So 3 to 1 is going to be the answer that we would look for this question. Right? The odds against it being a spade are 3 to 1. And then the probability of the card being a face card. So that's going to be the number of face over the number total, right? So it's going to be, what is the number of face cards? Well, there's 3 face cards for each suit. So 3 times 4 is 12. So it's going to be 12 out of 52, right? Which is going to be the same as 3 out of 13. Oh. My calculator is stuck in that wonderful stats thing. So 12 out of 52, I could do this and get about. So that's going to equal to, like I said, 3 out of 13, or about 23%. Okay. So Calais, that was turned out to be a bit more long-winded than I intended for that to be, but that is a look at your that is a look at the next unit as well. So I hope that gives you a bit of a background to use to approach those. Excuse me. I've got a few minutes now before I want to to my new normal quitting time. Well, my quitting time for Twitch, not nearly my quitting time for working. Pythagorean theorems up next. So Renetta, that'll be a few questions for the course that you're currently working on. Let me see here. That is, well, I got to use a few props today, didn't I? I've got some tidying up to do, right? Okay, so 1102C, Unit 1, page 311. Give me one quick second here. Here we go. Back over to my document display. Let's change my background. There we go. Let's go back to this one for a bit. This is going to be Math 1102C, I believe. Yes, and this is Unit 1. Okay, and this is page 311. 311, let's do question 1. Question 1A here. So, is angle Q in each triangle a right angle? Show your work. Well, what would be the case, right? So, we know that if So we need to test and see if the Pythagorean relationship is accurate for these triangles. So all we're going to do is just go through and then we're going to try one side of it and then see if it works out to be what the other one would be. Because if we look at this triangle over here, right? So 12 and 9 would be A and B because those always had to be the shorter sides. And then C squared, C would be 14 over here. So I'm going to try now 9 squared plus 12 squared. That's going to equal 81 plus 144. That's going to equal 225, right? That's right. And then, oh no, let me say x squared equals that. Okay, good. Yeah, this makes it work out a bit better. So then x is going to be the square root of 225, or x is going to be 15, right? And we know that 15 does not equal 14, so this is not a right triangle. Right? So that's what we had to do for these is see if it's going to work out or not. All right, so I'll do another few like this. And then I'll do a word problem or two, and that probably should be enough for a few examples for you to see how these ones are going to go down, right? So here again now, we're going to need to test and see. So we're testing to see if a squared plus b squared equals c squared is true. Camera, will you stop doing that? Boy, oh boy, it gets so dark. So then I'm going to say x squared is going to equal 30 squared plus 72 squared. So x squared is going to equal 900 plus, and I'm not going to do 72 squared in my head. 72 squared, 5184. X squared is going to be 6084. So then x is going to be the root of 6084. So x is going to be the root of that, 78. Right? And here, 78 equals 78. So this is a right triangle. Okay? Let's do one more of these ones because I've got enough space on the page for one more. Then I'm going to do a few word problems, and then that'll be it for today, I think. Unless someone drops in with some questions for me. Excuse me, my goodness. Okay. So we're going to test and see if those are true. So we're going to have x squared equals 15 squared plus 8 squared. X squared is going to equal, so that 225 plus 64. So x squared is going to be 289. X is going to be the root of 289. I seem to recall 289 being a root 289. Yes, that's 17. X is equal to 17. And then 17 equals 17. So this is a right triangle. Right? So that's all we're doing, basically. I know this is 17 equals 17, 78 equals 78. Like, why does Peter bother to write that down? That seems like nonsense. But I'm just showing that the value that we found does equal the value that's shown on the triangle. Same as over here, right? The value we found equals the one on the triangle. But up here, remember, the one we found did not equal the one on the triangle. Okay? So let's take a quick look at number 4 down here. Because number four is quite similar to ones that you are going to see on your tests and assignments and stuff. Hint, hint. Nudge, nudge, wink, wink. So this is math 1102C unit 1 still. Now we're on page 312. Question 4, part A. So Graham is building a workbench. He adds a diagonal brace between the tabletop and one of the legs as shown. He measures the length of the brace to check that the tabletop and the leg are square. The brace is 20 3/4 inches long. What should the length of the diagonal brace be so that the tabletop and the leg are square? What can Graham conclude about the angle made by the tabletop and the leg? Okay. So, in order for it to be square, well, what sort of situation do we have here now? We have a triangle. Just going to break out a diagram here. Just going to do a real small one, just like that. Right, so we know this is 14.5. I'm going to write them as decimals because writing them as fractions, that's not really the topic of this unit, is converting those. But I am going to write them as decimals, right? And remember, if you forget just what, say, 3/4 is, all it is just literally 3 divided by 4. See, in my calculator, when I do divide, it even comes up with the over symbol like that. 3/4.75, right? So we're going to test to see if a squared plus b squared equals c squared here. And that's how we're going to test and see if this is a right triangle or not. So we're going to have 14.5 squared plus another 14.5 squared equals c squared, right? So then I'm going to go do that. 14.5 squared. So 210.25 plus 210.25 equals c squared. 420.5. Oh, almost. Almost Twitch chat. It was almost dank. Root 420.5 equals c. That's going to be 20.5. We'll call it 20.51 equals c. Right? And of course, 20.51 does not equal 20.75. Therefore, okay, so this is actually part B now, kind of. 20.51 does not equal 20.75. Therefore, the table is not square. Because it tells us that the brace that he put in, and it went from here up to here, was 20.75, which is bigger than it should be, right? So we know that the angle between the table and the leg must be greater than 90 degrees. We know it has to be greater than 90 degrees because, oh, sorry. No, it must be less than. My goodness. I said the total opposite of what I was just going to mention, right? Because what we found was that, okay, no, see, I'm confusing myself here now. I'm confusing myself. Okay. We're almost done. Almost done for the day. We've got there, right? So just have to articulate the reasoning behind this question. We found that if the corner is indeed 90 degrees, then the measurement that should be there should be 20.5. So this should be 20.5 inches here if that is 90 degrees. But instead, this is 20.75. So it's an extra quarter of an inch bigger than what it should be, right? So if this is bigger than what it should be, it means this part over here is sort of pried open a bit more. So it's not 90 degrees. It's a bit bigger. So it does have to be greater. It is greater than 90, right? Because we found that if it was exactly 90, then this distance from here to here would be about 20.5. But in reality, the distance between here and here is 20.75, which means this piece is longer than it should be, which means this angle is pried open a bit more. So this is not actually square, right? A good way for him to square it up could have been to make this the exact length and then sort of squeeze it back, I suppose. But that's sort of forcing it to fit afterwards. It's probably to do with the cut, with the angle of the cut on the top of the leg, right? Depending on how we attach it to the table, of course. But something is off. Some of the angles are off somewhere. Not a whole lot, but a bit. Anyway, so that will be all my topics for today. All right, switch back over to this incredibly adorable picture here of little Flurry and Smokey out trotting around in some crystal clear water. Look at that. Oftentimes, yeah, I mean this is a very rocky island, of course, but we do have some silt sometimes in the bottom of of lakes and ponds and stuff, right? But very clear wherever that was taken. And of course, salt water is never that clear very often, right? I mean, sometimes it is, I suppose, but there's all kinds of stuff. Anyway, I'm just gonna stop rambling here now. Seeing my math part is done, and I've got plenty of other stuff to go get to. So, thanks for being here with me today. I hope it's been engaging and interesting, compelling, and yeah, I hope you stay safe out there. And I'll see you again tomorrow.